Okay, so chapter 19 is all about acid-base chemistry. There is some specific stuff he talks about in the study guide with regards to benzoic acids, which I'll go into. The part that he started out with chapter 19 was the Henderson-Hasselbalch equation. That was where he derived this relationship between pH and pKa. So if you understand the Henderson-Hasselbalch equation from Chem 106, you can use that to derive this relationship if you forget it on the exam. But I think the relationship's easier. If you can just remember that, then I wouldn't worry about deriving the equation. But I just wanted to bring it up. You can use it if you forget. But basically, from the Henderson-Hasselbalch equation, we learned that the pKa, if the pKa is greater than the pH, then that group that pKa is referencing is going to be protonated in that solution with that specific pH. And that means that it's going to be positively charged. So that means it's going to have as many hydrogens as it needs to be positively charged. So if neutrally it has a hydrogen on it, then when it's positively charged, it's going to have 2 hydrogens on it. And I'll show you an example of that in a second. And then if the pKa is less than the pH, then it's going to be negatively charged or deprotonated at that pH. So if it has a hydrogen when it's neutral, then it's going to be a negatively charged, no hydrogens when it is lower than the pH. And then if the pKa equals the pH, then it's neutral, or in its stable state. So if an OH, for example, an alcohol group, neutrally has a hydrogen on it, so it will have a hydrogen on it if it equals the pH. And this actually will become really helpful for you in biochem, so make sure that you understand this relationship and that you can apply it to molecules. You'll have pretty large proteins when you take biochem and have to do this, and you'll usually use titration curves to do this. So I would make sure that you get this down. It's really easy if you understand it. So a caution is that the structures are often listed in their neutral form in the charts for pKas. So just make sure that you're focusing on the pKa, not the structure that's drawn, when you're trying to relate pH and pK. Does that make sense? So you're going to have a chart of pKa's listed, but you're going to have different pHs that you're given. And so each pH, they're going to have a different protonation state based on their pKa. So don't get hung up on what the structure is drawn on the chart. The structure is going to change based on its pKa related to the pH of its solution. Does that make sense? Yeah.
So do we do all functional groups? Do you look at every single one of the molecule?
Yeah, and on the exam it's going to be a pretty large molecule, so I would make sure that you're very, very careful in how you account for all these. How I did on the exam was I just found every single functional group and circled them and made sure that I had found them all. And then I went to the back of the test where you have your pKa chart, and I wrote all their pKas on next to them, so I knew what all of them were. And then he'll give you he'll give you a few different pHs, like evaluate the overall charge of the molecule at a pH of 4, 7, and 12. And that it changes based on all their pKas. So then at each pH, I would go through and evaluate if that group was going to be positively charged, negatively charged, or neutral at that pH, and then I added them all up at the end. Yes?
So, like a carboxylic acid has a pKa of around 5, and if it's in a pH of 4, it would get protonated, but its conjugate acid is -2. So do we have to take into account the conjugate acid's pKa too?
Oh, I see what you're saying. I would just consider it in its neutral form as a carboxylic acid with a pKa of 5. Does that make sense? Yeah, I wouldn't consider, Because there are different states that all of these functional groups can have, and they change their pKa's based on the states in which they are. But in their neutral form, that's the pKa that you'll be given. And depending upon that, that's how things will change. Yeah.
So like in that example,
Mhm.
the carboxylic acid would have two H's,
Mhm.
protonated and positive charge.
Mhm. Yeah. I'll do like a little example of this. I've done it in my recitation, so if you've seen it, I'm sorry. But it's going to be a huge molecule. I don't want to draw it because it'll take too much time. But imagine a big molecule with an NH2 group on it and a carboxylic acid. And you're asked to evaluate the pKa at a pH of 3, a pH of 7, and a pH of 13. And you know that the pKa's of this are 11 and 5. So what is the overall charge of this molecule at each of these pHs? The first thing you should do is consider each of them individually and how they would be at that pH. So at a pH of 5, this one is going to be positively charged, right? So it's going to have 2 hydrogens and a positive. This one is at a pH of 2, or a pKa of 2. So at a pH of 3, it will have lost a hydrogen and become negatively charged. Yeah. Oh, sorry. This one's still positively charged. Sorry.
Because it would be 11 pK.
Yeah.
Bigger than 8.
Sorry, I saw the 2 next to the hydrogen and freaked me out. Sorry. So both of these would be positively charged, right? Which means the overall charge of that molecule is a positive 2. Yeah?
I thought the pKa for carboxylic acids just referred to change between negative and neutral charge. I didn't know. Like I thought if the pH is below 5, doesn't that mean that it's just OH?
No. So that's where the Henderson-Hasselbalch equation comes in, where it has to be positively charged if its pKa is greater than the pH, because it will be in its protonated state at that point. Because what the Henderson-Hasselbalch equation is telling you is that you have more protonated, not so much neutral molecules, but protonated molecules compared to the unprotonated ones.
So I guess I thought the protonated form was just when it had OH on it.
The only time when the OH is considered is when the pH and the pKa are equal to each other.
Okay.
So this would be just OH at a pH of 5. Because you have an equal portion of unprotonated form and protonated form at that pH.
And how could you have like a neutral charge on the overall this Twitter ion or whatever it's called?
You can, which is this next
Okay.
one. Because this one's pKa is less than the pH, but this one's is still greater. So this one will be completely deprotonated at a pH of 7. And that will be negative charge. But this one's still protonated, so this overall charge is going to be 0. And then at this pH, both of these are now lower than the pH of solution. So this is going to be deprotonated, have a negative charge, and this will be negative 2. Okay? Yeah.
What's the only type of question that would be asked?
Yeah.
This?
Yeah. And it's going to show up basically exactly like this. This type of question. Yeah.
So if you have 3 and you had 1 that was like positive and 2 that were negative, then it would be negative 1.
Uh-huh.
Okay.
Yeah.
Just making sure.
No, yeah, you're fine. So you add up all the charges. It won't be like any big massive charge. If you're coming up with like a charge of like +7 or like -12, you're doing something wrong. So it's gonna be like a lot of them are gonna end up canceling out. You're gonna have a lot of functional groups that end up canceling, and you'll probably end up with something around within the ±3 or 4. So I would not expect something like a very large change in charge. Yeah.
Do you not want to consider like H3
No. Yeah, because I would worry about the functional groups that are involved. Yeah.
Sorry, I guess maybe not asked this already, but did you say like the molecule is always going to be like in the neutral state like when it's given to us? Like I think what you're saying about like the select acid, like it'll start with the OH group on it like when we get it, and then
Yeah.
we decide whether we're going to add hydrogen or something.
Yeah.
Okay.
So what this little caution is saying that the chart is evaluating the molecule as if the pH were equal to the pKa. So the molecule would be in its neutral form. That's how it's often explained in the book, at least. That's how it's often presented to you.
Will he give us the pKa for different functional groups?
Yeah. Yeah. You don't need to memorize pKa's for functional groups. He has a chart that he'll give you for all the ones you need to know. Yeah.
So when you say the little caution, you just take the pKa of the chart, like it doesn't matter.
Yeah. I just wanted to give you this caution so that you guys knew that even if the molecule did not look exactly like the chart, at different pHs, that's okay. That pKa is what you use. Okay. Other questions on this? Okay. All right, and then this is just a review of acids. The stronger the acid is, the lower its pKa. A strong acid is strong because its conjugate base is more stable and can tolerate extra electron density. And weak acids are weak because their conjugate bases are less stable and cannot tolerate extra electron density very well. So understanding this will help you with acid-base chemistry, but applying these to carbonyl compounds and leaving groups is also effective. So, which I'm sure you've already been practicing with the practice exam and stuff. And then a review of bases. The stronger the base, the higher the pKa of its conjugate acid. A base is strong enough to deprotonate any acid whose pKa is lower than the pKa of that base's conjugate acid. So this is why you can't react a conjugate or a carboxylic acid with anything with a pKa, a conjugate acid's pKa of greater than 5. Because if you have a pKa of 11 of your base, for example, it's just going to deprotonate your carboxylic acid because its pKa is 5. So the reaction will always go from lower pKa to higher pKa. So that's why you want to have a low pKa as the conjugate base's conjugate acid, or the base's conjugate acid. Does that make sense? Questions on that? We'll talk a little bit more about the special case for carboxylic acids, but this is where that comes from. A base is only strong enough to deprotonate any acid whose pKa is lower than the pKa of its conjugate acid. If its conjugate acid's pKa is lower than the acid that it's working with's pKa, then it won't deprotonate it. Another reaction will occur. Yeah?
So if you had NH2 as the base, you'd have NH3 as the conjugate acid.
Mm-hmm. And then more stable conjugate bases stabilize a negative charge or a lone pair of electron density by holding the electrons on an electronegative atom or in a low energy orbital, spreading out the electrons via resonance, spreading out the electrons via an inductive effect due to nearby electronegative groups, and spreading out the electrons by holding them on a large polarizable atom. So the way that I would see this being tested is just the type of questions that you were getting on the very beginning of exam 1, where it was like, evaluate these different groups. Which one has more acidic groups on it, or which group has more basic groups on it. These are the ideas that you need to remember for those types of questions. Yeah?
I think there was a question on the homework involving like electron withdrawing groups and electron donating groups.
Mm-hmm.
Is that what you're talking about?
I actually am going to talk about that in a second. I'm pretty sure it's on these slides. But that's just bringing back the idea that if you have benzoic acids, the electron donating groups will destabilize them because they put electron density near the negatively charged oxygen once the hydrogen leaves. Whereas electron withdrawing groups induce a positive charge inside the ring, which stabilizes the negative charge on the oxygen. So that's where that comes back in, so I wouldn't forget that. Okay, any questions on this slide? Good? Okay. Alright, that's really all for chapter 19 that you need to remember. So, at least that's all that I gathered from his notes and his slides. All he really talked about in his notes was the pKa and pH.
Sorry, just going back real quick, like on that last slide, an electron withdrawing group will stabilize the acid or the conjugate base?
The conjugate base.
The conjugate base.
I tried to Google the acid, and the picture would not come up. So imagine this in its deprotonated form with a negative oxygen here, and that's what I meant to try to find on Google. But I
And
couldn't
when
find
you say electron withdrawing group, it's like another thing
Yeah.
on the ring?
Yeah, because technically this is an electron withdrawing group, but some electron withdrawing group on any of these other carbons. Okay, chapter 22. So chapter 22 is where we start getting into carbonyl chemistry and attacking carbonyls. It's important that you guys understand these concepts as well as understanding the backbone mechanisms for these things. I do apologize for not being able to make a chart for you guys for these reactions. I discussed it with Dr. Price and I decided that it would probably be better for you guys to understand conceptually more than me just spitting out a chart. So I hope that was more helpful for your studying, and I am sorry if it inconvenienced any. So the attack of the nucleophile, you need to consider first the strength of your nucleophile. So the strength of the nucleophile, if its conjugate acid has a pKa of greater than 16, then it is a strong enough nucleophile to attack the carbonyl carbon without any type of protonation on the carbonyl oxygen. So examples of this are like anything that's usually negatively charged, you're pretty safe with, like an OH minus or an OR minus. Also, I wanted to point this out. This is something he talked about in the very, very beginning. Sorry, there should be a parenthesis there. But he talked about this in the very beginning of carbonyl chemistry, and I thought it was actually really nice of him, that H minus and R minus, those are synonymous with reduction reagents and organometallics. Those also don't need any type of oxygen protonation. So that's a connection you can make with things that you learned later on in the chapters. So you don't need to protonate oxygens there. However, if you have a weak nucleophile, which its conjugate acid has a pKa of less than 16, then you need to protonate the oxygen first. Examples of this are like NH3. You don't have to worry about CN minus, that's one of the reactants that you didn't need to know, so don't worry about that. But like sulfur, a negatively charged sulfur, water, or alcohol, those things are examples of protonating a carbonyl oxygen. So that's the first thing you need to address every time you're doing one of these questions is what is the strength of my nucleophile and do I need to protonate it or not? And then you need to consider the fate of the tetrahedral intermediate. Oh, before I go on, I might talk about this later, but I wanted to also put a plug here for the carboxylic acid idea, that carboxylic acids have their hydrogen. And you guys have done homework problems on this, so this shouldn't be like a new idea, but like this hydrogen has a pKa of 5, which means you have to react it with a nucleophile which conjugate acid's pKa is less than 5, so that the acid-base reaction doesn't happen first. And if you do that, if you have to have a nucleophile with a pKa less than 5, then you have to protonate this oxygen every time. Every single time. Because we already talked about the fact that you have to have, if you have anything with a pKa of less than 16, then you have to protonate the oxygen. So if you need something less than 5 here, then you for sure need to protonate the oxygen, okay? So carboxylic acids, you always do carbonyl oxygen protonation first. Okay, questions? Okay, the next thing you need to consider is the fate of the tetrahedral intermediate. So Once your nucleophile attacks, you kick electrons from the carbonyl double bond up to the oxygen, and you have 4 groups bonded to a carbon. So you need to compare the groups. If you have no good leaving group, then you do aqueous workup, which is just putting water into your solution to protonate the negatively charged oxygen, and you're left with an alcohol. If the Y group, or if the nucleophile is the best leaving group, then you just go right back to the starting material. So you often won't have something like this. There's other ways to work around that. So if you have, like, the only way that he would test you on this type of concept is like, why can you not react this with this carbonyl compound? And the answer would be because it's a better leaving group than anything that's on there. But there's ways, which I am about to talk about, where you can actually make a good leaving group a bad leaving group, and make a group on the tetrahedral intermediate a good leaving group. So don't just assume that you're not going to make anything. If the Y group, which is the original substituent that was on the carbonyl, is a good leaving group, then you reform the carbonyl, kick off the Y group as a leaving group, and your nucleophile has substituted in for that group. And then if the Y group and the nucleophile are both good leaving groups, then you can use catalytic acid to make the Y group a good leaving group and the nucleophile a bad leaving group. So this is like H2SO4 or water and some type of acid. He's used catalytic acid like TSOH, but that's going to be for acetal formation. But things like that I would be aware of. That's how you can also use those for if your Y group is a good leaving group. You don't have, yeah.
Can you give a very brief example in the board case of
Yeah.
this?
Yeah. So, is everybody okay if I erase this? Good? Okay. So, if your tetrahedral intermediate looks like this, for example, this could be a good leaving group, and so could this, especially since it's positively charged. So you can have some catalytic acid come in and deprotonate this. I'm just going to do it real time really quick to save some space. And then you have that unprotonated, and you have your acid reformed. The other problem is, and also the reason why that was deprotonated is because you had to protonate that oxygen the very first for this to even attack. Okay? So we're assuming that's protonated. So once this is neutrally charged, this is technically a better leaving group at this point, but you usually want to make it a little bit of a better leaving group so that it will push the reaction forward. So oftentimes you'll protonate this first. And then you have this deprotonated acid in solution. So then this is positively charged, and then you can take this hydrogen back, push those electrons down here to kick this off. And then you've formed
In this case, we form with white.
yeah.
Sometimes, like in some reactions, we form a hydrate. When would the hydrate stay? Because like we have a hydrate as an intermediate here, but when does it stay as a hydrate?
I think you'd have to have more information to know. I think you'd know enough. Like, I don't think he would react. I don't think he'd give you this nucleophile if he wanted you to make a hydrate. He'd usually give you water, because water is usually what you use to make hydrates. So there's certain things, like there's certain conditions that can clue you into what he's trying to help you make. Here, you'd know pretty quickly that he wanted you to make an amide. So, yeah. Whoever wants to go first.
Just wondering if it's necessarily they're both really good leaving groups, or just if they're kind of similar. We have to know like specific names and such.
You could use PKs to answer that question, but you don't need them. He's often used that rationale as well, that as long as it's about as good as a negatively charged oxygen, then it's a good leaving group. If you've been using that and it's been working, that's fine. That doesn't always help if you have to kind of change things up to get the correct one. It will always happen this way. If they're both good leading groups, he wouldn't just have you react with the nucleophile and kick it back off. So this is the way in which he's taught you to take the nucleophile, make it a poor leading group, and then make a good leading group out of the other group. Yeah.
So just connecting this to what you just said about carboxylic acid. So your starting material would have been a carboxylic acid, right? And then you would have protonated that to get to the point where you would put on the nucleophile.
You're right. I'm sorry. You're right.
Because you're looking at the picture you're drawing.
Yes.
But I'm just like, for
Yes.
the starting material.
I'm gonna change this. I'm really sorry, you guys. I hope this doesn't confuse anybody. I'm gonna make this this. And I guess here it doesn't really work. You're right.
No, you're good. I'm just making sure.
This wouldn't have worked with the carboxylic acid. You're right. Because its pK is 11. So even if I protonated the oxygen, it still would have deprotonated that carboxylic acid hydrogen, no matter what. Does that make sense? So I had to have had, so I guess maybe changing my nucleophile would be a better idea. I'm trying to remember one that,
Like an ester.
yeah. Well, no, even then it's a 16. I'm trying to remember. Does anybody remember off the top of their head a nucleophile that you reacted in your homework
Well, with
to a
ester
carboxylic?
certification, you have like a.
Yes. Yes, yes. 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 So this would have worked. And you're right, with ester esterification you can do this one. Yes. I hope that didn't confuse anyone. Does anybody have any other questions? Okay. So an example of this is esterification using carboxylic acids, which is this. And you use acid. And then ester hydrolysis is just esterification in reverse. Okay. And then fats and lipases, this was an example of ester hydrolysis. Do you guys remember when he started talking about like the catalytic triad? I think it's really cool that he like shows you guys this stuff. I know it might seem like a lot of extra information you don't actually need to know, but it's a really good intro into what you're going to learn in Biochem at 481. Like you're going to have to know all the details about what the catalytic triad is and what it does and how it's useful. So I would just remember that it was used for ester hydrolysis. It was a way for an enzyme to cut fats and proteins away, or cut them up. And then saponification is specifically hydrolysis of esters with an OH minus instead of with water and acid. So, yeah. Okay, then acid chlorides, those were how to, they're basically really, really good at doing nucleophilic substitution. So you're going to basically see a substitution with any of these nucleophiles because of chloride's pK. It's such a good leaving group that if you react it with a carboxylate anion, you make an anhydride. If you do anything like a negatively charged alcohol or a protonated alcohol with a base, you're going to create an ester. If you do an OH minus, it will be carboxylic acid, and then an amine, you'll create an amide. So they're pretty versatile in creating what you need. Yeah.
The book it says for the amines you need 2 equivalents to make the salt.
He often doesn't really care about the equivalent stuff. I would just assume that you have excess of your reagents unless he's very specific about how many equivalents you get.
With the
Yeah. Yeah, unless he specifically says you only have one equivalent of an organometallic reagent, which oftentimes you don't. Like, there's no way to, in a lab, get one equivalent of an Li and an organolithium reagent. So it'll go all the way to the alcohol. A lot of people have asked me that for synthesis. If you want to stop at the aldehyde, can you just use one equivalent? But there's no way to just get one equivalent. Like, it will happen all the way to the alcohol. So assume that, especially for organometallics. Unless he specifically says you only have one equivalent of this reagent, you have plenty. Okay. Carboxylic acids, we already talked about their special conditions. If you need to make an acid chloride, you can use carboxylic acids with Sockle. You guys remember why Sockle was a adequate use, like an adequate reagent to make an acid chloride? Yep. Yes, thank you. So it supplies the nucleophile. It also changes the OH to a leaving group. And it is a better leaving group than chloride by itself because it creates SO2 and a chloride ion. So not only is it creating a chloride ion, which you would make if you just kick the chloride right back off, but it also creates a gas that bubbles off of the solution, so it pushes Le Chatelier's principle forward. Okay. And then if you want to change a carboxylic acid to an amide, which is what we were doing, you would need DCC as well, which is what I forgot to do.
What did DCC do again?
So basically what happens with DCC is you deprotonate your carboxylic acid. You harness the fact that it will be deprotonated by an alcohol or something. And then you put DCC into it, which it attacks as a carboxylate anion. And then it makes that oxygen that just attacked it a good leaving group. And then the amine can come in and attack it and pick it off.
Do you know where we can find the mechanism?
It's in his notes. He did arrow pushing for it. I don't think you need to know it. I just think you need to know that it's a carbon that's double bonded to 2 nitrogens. So they induce a partial positive charge on that carbon, making it electrophilic. And then there's resonance within DCC, so it makes it a good leaving group. Other questions? Yeah.
Sorry,
You're
you
fine.
did show the mechanism of the SOCs doing the same.
Yeah, you don't need to worry about it. He did show it for DCC, so I would just familiarize yourself with it if you need to know it. But I think the only important arrow pushing you need to know for DCC is just that there's resonance within that molecule, which makes it a better leaving group because of the double bond character that's there. Okay, chapter 20. We are just cruising right along. I love it. Okay. So in chapter 20, we talked about reduction reagents. Yeah.
Sorry, I forgot to ask one last question. On the
Yeah.
last part. The acid to amide using DCC, what does that DCC work on exactly?
So you're assuming that you use DCC with usually some type of alcohol or something, an organic solvent. You're just gonna assume that the organic solvent is gonna deprotonate. Actually, not this one. Like, let's say you do. I can't remember exactly what he uses, but something to deprotonate the carboxylic acid. Imidazole. Is that kind of what you're gonna say? you're right. Yeah. So there is a nitrogen within the DCC that can deprotonate. You're right. Does anybody have any? Everybody agree with that? Okay. So DCC is going to deprotonate this. So we're just assuming this is deprotonated. Okay. And then you have this DCC, which looks like this. And then R groups, which are really just cyclic cyclohexanes. And this has a partial positive charge, so now this can come in and attack this. And once this attacks, this kicks up to one of the nitrogens, and then now you have resonance within the molecule that can cause it to be a really big group. I don't think you need to know arrow pushing for this, so I wouldn't worry about it, but I would remember that the reason why you even use DCC is because it makes that oxygen a good leaving group. And since you do have amine in solution, they're going to deprotonate that carboxylic acid anyway. So you're harnessing that deprotonation to actually make what you want anyway.
And then the amine will come in.
Mm-hmm. Yeah. So then the amine can come in and attack the carbonyl carbon. Okay. So in chapter 20 we talked about reduction reagents. LiAlH4, that's the one that doesn't stop at the aldehyde or the ketone. So whenever you have that, it's going to go all the way to the alcohol, and it adds 2 hydrogens to push it that way. And it doesn't need to protonate the carbonyl oxygen in order to do that. The big long reagent that I won't say the name for, and dibol, those are the ones that will stop with the aldehyde. So both of these will react with the same things, esters, anhydrides, carboxylic acids. They will react with them, but they won't, but this one will stop, this one will go all the way. NABH4 is the one that will reduce aldehydes and ketones, but they won't react with anything other than aldehydes and ketones. So a way that he could use these is he could actually use dibol and NABH4 together to create the alcohol from an ester, for example. So you can use them together, and oftentimes they do use them together in the lab just because this is such a reactive molecule that can I think he said something about it reacting with air to blow things up. So oftentimes we'll use these less reactive ones to get to the same product. Yeah.
So you would just use dibol here for the aldehyde and then NABH4 to get from the aldehyde to the
Alcohol. Mm-hmm. So that's the way you can see it. Yeah.
For some reason, I'm having a hard time knowing what the difference between the LA and ALH4 and the NADH4. They both don't stop. But is it that NADH4 just isn't as strong, so it can only do these downsides, but LA could do anything?
Mm-hmm.
Okay.
Yeah.
Cool.
Okay. Other questions on reduction reagents? Yeah. No. So LiAlH4 is a specific one that he said you can't use water because it's so acidic that it's going to deprotonate water before it ever does any type of reaction with your carbonyl. So I would just assume this is not in water, the most reactive one. Yes. Yeah. So once it's all the way reacted, usually what happens is in the lab, you have some type of way to figure out that your reaction's to completion. It'll change color, or you'll have a color indicator, or it'll change temperature. Something will happen in the reaction that will tell you it's finished. It'll stop bubbling or something. And then from there, you can then put water in it to protonate your alcohol. So you will do aqueous workup, but you're assuming that that's after the hydrogen has completely reacted with your carbonyl. It's hard to, I know a lot of people say not to do the OChem lab with this class, but I actually am an advocate for it because it's really cool to be able to learn this stuff and then to actually see it done in real life. But because you do this stuff in the lab. You don't use ALH4, of course, but you do stuff like this. So. Okay, organometallics. So organolithium and Grignard. Grignard is the one where it's like the alkyl group with NGBr. That's what Grignard is. Yeah.
We need to be able to build these.
I would just assume that I'll go over it. You don't have to know mechanistic steps for how to build these, but it would be helpful in synthesis. Basically, I don't think you'll need to know how to build this. I think if he wants you to use this in synthesis, then he'll tell you how to make it. He'll just tell you to have it. But like this can be used interchangeably with the organolithium, so I'll just show you how to make that because they do the same thing. Basically, to make an organolithium, you just take a halide, like a alkyl halide, and you react it with lithium. And it just switches out your halide. So, that's the easiest one. Thank your lucky stars that you did not have to learn how to make these, because majors have to know how to make these. So, I am jealous of you. Because it's not that much, but it's just another mechanism to know, you know. Anyway, so if you need to use these in synthesis and all you have is alcohols, you can make an alcohol into this with PBr3, and then you can make it into a Grignard if you need it, organolithium. They go all the way to the alcohol. They don't stop at the aldehyde or the ketone. And a pretty good indication that you probably used this is if you have two groups that look exactly the same on an alcohol, then that's a ding 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 that was made with an organolithium or a Grignard. So those are really nice when you can see that on the test. You're like, oh yes. Yeah. So if you see an alcohol with two identical groups on it, that's like a clear indication that you use organolithium or a Grignard reagent. Also, this synthesis is going to be difficult, but it's not going to be like Michaelis difficult for those who had Michaelis. His synthesis were like, holy crap, like so hard. All of us TAs, he did not even let us grade those because they were so hard. He was like, I'm the only one who actually has the knowledge to grade these correctly. So we're like, okay, well that's probably not very nice of you. Anyway. You guys still did really well because he was really, really kind about grading it. But it's not going to be as hard as that. Do you guys remember the questions on the exam, on exam 1, that had just like different lists for the aromatic substitution? That's like the only way that he can write a synthesis question, really. So like if you can confidently go through a list and be like, this will not work for this reason. And they're gonna be pretty, the reason why I say they're hard is because there's not gonna be very many things wrong with them. There's gonna be maybe one that's like, okay, there's no way in any universe that this would work. But there's some that they're gonna be like, oh, that could work. It's just sometimes you have to go all the way through the list to find the error. But if you can confidently go through lists like that and be like, okay, for this reason, this list will not work, you'll be fine on the synthesis questions on this exam. So that's really the only question you can ask. Another question I can think of is that question with different arrow pushing on exam 1, and it was like which one's the right step, and for each step there was something that you needed to know that made it wrong. So that's the extent of these questions. So I wouldn't be riddling yourself with stress about synthesis, but just know that that's kind of the format that you'll see it in. And I'll talk a little bit more about synthesis when we go forward. And then organocuprates. There's some really specific things about organocuprates that you'll need to know and that you will get tricked on if you don't know them. So the first thing is they have two identical R groups on them, but they don't add both of them when they attack. They only add one of them. So they stop at the ketone or the aldehyde. If you don't understand that, then you will probably end up adding both and you'll get to the alcohol and that will be wrong. Okay? And the alcohol will be an answer for these. So don't mess that up. It stops at the ketone or the aldehyde and it only adds one of the two identical R groups. Okay? Yeah? wish I knew. Really, all I can say is that copper is just not strong enough to be an effective nucleophile deliverer. That's all I know. Because aldehydes and ketones don't have good leaving groups. They're pretty stable. So you have to have a pretty strong nucleophile deliverer to do that. That's all I can say. That's very hand-wavy, but that's all I got. Yeah.
Strong word would be by it has to identical R?
Yeah. So an example of that could be like, so they're exactly the same. Like literally exactly the same. There will be nothing different about the groups on these. That's just how they have to be made. And again, if you had to know how to make these, then that would make sense. But like in making these, you learn that you can only add, like you have to add them identically. So, okay. Alpha, beta, unsaturated ketones. I'm actually pretty proud of myself that I figured out where the alpha and beta things were. They're really pretty, huh? Okay, anyway, it's really not that hard. It's like a special characters section. Anyway, so the alpha, beta, unsaturated ketone. These are super important to understand because it's really easy to trick you on this if you forget. So like, please don't forget. Organocuprates will always attack the beta carbon of an alpha beta unsaturated ketone. And they look like this. Okay? Where you have your carbonyl carbon, alpha carbon, beta carbon. They will always attack the beta carbon every single time without fail. Which means that anytime you have an organocuprate on the test, anytime, you should immediately go back to your molecule and find the alpha beta unsaturated ketone. If it's not there, then just react it with the carbonyl carbon and you're fine. But if it's there and you miss it, then you will get the question mark. Okay? Yeah?
I think you said in class today that it doesn't matter if the beta carbon is part of a cyclic compound, right? If it's like a second butene, it doesn't matter at all.
Mm-hmm. Yeah, it still is the beta carbon that it attacks every time. So just that was like something that saved me on this exam. Was like every time I had an organocuprate, I would immediately go find my alpha beta unsaturated ketone, and it oftentimes was there because he wants to test if you remember this part. So yeah.
So if there is no alpha beta unsaturated ketone, the organocuprate will attack the carbonyl.
Yeah, it will. But it will stop at the, well, I guess you're right. If it's a cyclic compound, no, because then it's just a ketone at that point, and it doesn't attack ketones.
Okay.
But if it has a good leaving group, then it will attack, yeah. But in like a cyclic compound where it's just a ketone, it won't attack. Yeah, which is an example he gave in class. Yeah.
So just to like make sure,
Yeah.
can you show an example of that organocuprate that you drew on the board attacking that alpha beta unsaturated ketone?
Yeah. So it will come in. Basically, these electrons will pop up on here, on the alpha carbon. And this is where this last part happens, the protonation point on there. You induce an electrophilic carbon at the beta carbon. So this comes in and attacks right here. And you form, sorry, I want to try and not stand in front of the thing. And then you can either protonate this and just create the ketone, or you could kick these electrons up, kick these down, and protonate the oxygen. But if you protonate the oxygen, then you're going to create an enol, which will tautomerize anyway.
So what will it end up as then?
It'll end up as the ketone every time, yeah. But if you if you like to move the anion down instead of protonating the anion, you can. Just remember that you do need to tautomerize the enol that you make. So it just makes more sense to protonate that anion anyway, because that's what you're ending up with. Because basically, just having like something in solution, you'll probably have some type of water that you can protonate that way. But like, if you think about the mechanism of tautomerization, it's literally just kicking those electrons right back to where they were, and then taking that hydrogen and just putting it there. So you might as well just protonate that and save yourself some time and some, yeah.
I've asked a lot of questions, I'm sorry.
You're fine.
Maybe this is a dumb question. If you're gonna attack the beta couple in that case, wouldn't you use was it an organic cuprate, not lithium?
This is an organocuprate. This is the one that I'm attacking with, this one right here.
Sorry.
An organocuprate does have lithium like participating, but it's copper that's the covalent bond.
I confuse those. My bad.
You're okay. Another thing I want to say, this could be a why question on the exam. He talked about it and he made a point to emphasize it. Organocuprates are covalently bonded. So don't forget that. Like, it's not an ionic bond where there's like a negatively charged carbon and a positively charged lithium hanging out together, like NaOH, for example. NaOH is ionic, but Li and its alkyl group are covalently bonded together, but they act as if they were ionically bonded. So the anion will go and attack, and the lithium will stay away. Okay? So just don't forget that. That can be a why question. Yeah. So you're okay. So in class, he's often talked about that this can also be considered this. And you can just consider that the anion is going in and attacking. But that doesn't, like, this looks like an ionic bond, but it's not. They are covalently bonded together, but they act like an ionic bond. Yeah.
Yeah, for both cuprates and lithium.
Yep.
And,
Right here. Yep. Yeah.
But in the organocuprate, the lithium on that one is just an anion.
Yes. But the copper and the alkyl group are covalently bonded together. Yeah. So in this case, this one is just hovering as an ionic bond, but for the most part, there's covalent bonds involved there. Other questions? Yeah.
You have an ester like that up there, but it has but it doesn't have, just like that one, it doesn't have a beta. Is it organic cuprate strong enough to attack an
Yes, only if there's a good leaving group. So like an ester, for example. Yeah.
So chlorine, what else is strong?
An ester, carboxylic acid, no, because of its character. What?
Wait, you said
Anhydride. Carboxylic acid, I don't think. Yeah, would just deprotonate because lithium reagents are so basic.
it's basically chlorine, ester,
Anhydride.
anhydride. That's about it.
Yeah. Okay. Other questions on organometallics? Okay. And then, wow, I got really, how did that happen? Okay. Again, please make sure you understand this because it will come back to bite you if you don't. Okay. Protecting and deprotecting alcohols. Don't get these mixed up with acetals. Acetals are for protecting ketones and aldehydes, which I'll talk about in a second. When you're protecting an alcohol, you use silyl ether, which is very confusingly abbreviated as TBD-MsCl, which I think takes longer to say than silyl ether, but alas, here we are. So, TBD-MsCl with imidazole. Make sure you have a base because you have to deprotonate the alcohol that you're protecting. And then, does anybody want to answer why we protect alcohols? Like, why do we even do protecting groups? Yeah. Yeah. Acid base will happen quicker. And oftentimes when you use a protecting group, it's because the product that he gives you has an alcohol that was not reacted with at all, but a different portion of the molecule or a different alcohol. A different portion of the molecule, like a ketone or something that was reacted with. Yeah.
Will this react with anything that's feedback? Like if you're
The silyl ether will attack the oxygen,
Yeah. Once your alcohol group is
protected,
it won't react with anything.
except T. Yep. 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 Okay. Questions on this? Pretty self-explanatory. It'll probably just be a list of reactants, so you'll have to pick it out. Alright, this is where I just wanted to put a plug in for synthesis practice. I thought this was really nice of him to like take time in class to just like straight up basically tell you exactly how he's going to write the question and exactly how you can get it right. So again, you're going to get a molecule like this, probably a little bit harder than this, I would say. It's hard, but it's not as hard as he could come up with, I'm sure. But like, he went through all of the ways in which it's important for you to pick out. He'll give you like, you have an aldehyde and you have alcohols of 3 carbons or less, like the practice exam had. And you need to pick out, it's the same type of thing as synthesis that you're used to. You look at the molecule you have, you find the parts of the molecule that you could have made from your starting materials, and then you work through making the starting materials into what you need. But again, you're not going to have to like reproduce this on an exam because of its multiple choice nature. You'll just have to understand very key concepts about each of these reagents, how they react together to make molecules. So, questions? I just put this up so that it's an example of like I would go back through his notes if you're struggling with synthesis and look at how he reasons through all these. Okay, chapter 21. This is where we talked about protecting or deprotecting ketones and aldehydes. This is where acetals come in. And really all the acetals are is like reacting an alcohol, deprotonating it, protonating the oxygen, the carbonyl oxygen, enough to make it water and leave, and then letting another alcohol come in after you've reformed the carbonyl. So it's just like a lot of deprotonation and protonation and leaving of water. So as long as you're comfortable with like using acid to deprotonate and reprotonate things, this shouldn't be too difficult. If it is, let me know. But the reason why we use acetals as protecting groups for these is because they're not good electrophiles and there's no acidic protons. So they are stable in the presence of strong nucleophiles and strong bases. So if you have these and you need to keep your aldehyde or ketone from reacting, like if your ending product has that ketone unreacted, that's probably not going to happen because of the reactivity of a carbonyl carbon unless you protect it with an acetal. Does that make sense? Questions on that? Like it will react because of its reactive nature unless, especially in the presence of a strong nucleophile and a strong base. And don't forget to remove water. He talked about that a bunch in class. Like every time he did acetal or anything with regards to kicking water off, you remove it, or else the backwards reaction will happen just as quickly. So you need to, especially since the deprotecting reaction is acid and water. So you use acid and alcohol to make the acetal. If you don't remove water, the deprotecting is water and acid. So you need to take water out. And usually you do that with salt or boiling it off, but I don't think you need to know that. But just remember that. Don't forget to take water out. And don't forget to remember why. Like there's a reason why. It's because you don't want the backward reaction to occur. Deprotecting with acid, again, also the acid that he uses for this is TSOH. Don't forget that. TSOH is the acid he uses in class for acetals. Deprotecting with acid, usually he just uses H3O plus in water. Basically, if you have TSOH in solution and then you put water into it, there will be H3O plus in solution. So H3O plus is often just saying there's acidic environment, there's acidic protons in solution. And then the acetal turns to the aldehyde when you deprotect with acid and water. So it's basically just the opposite. You have water attacking, and you're protonating the alcohol groups to kick them off. Questions? Also, something that I just thought of, it's important as well to make sure that you remember that you can't just like kick groups off. I know in SN1 reactions that we learned in 351, if you have like, you needed to make carbocations in order to do SN1s, but I would just remember, because you might get mixed up and start making alcohols when you don't need to. In order to kick a group off, you have to have some electron density pushing them off. So you have to have the electrons coming off of the negatively charged oxygen back down into the carbonyl, or you need to make a carbonyl with the alcohol oxygen for an acetal. You need to recreate the carbonyl in order to kick leaving groups off.
As far as multiple choice questions go, can you maybe give us an example of how you process on this concept of acetals?
The way that I would see it is probably like which mechanistic step is right. Another question you can ask is which one is wrong. There could be like 8 different steps. One of them is wrong for some reason. The other ones are totally viable for an acetal reaction. So things like that. He could also ask you like why questions about this. I don't know exactly what he would ask, but he went into great detail about these mechanisms, so this probably would be a mechanistic type of step. Yeah.
Sorry, back to like the TSOH. Was
Yeah.
it TSOH or water and H3O plus?
H3O plus is what he used to deprotect it. TSOH is what he used to protect it. But it's really the same in the end. So like it's okay if you use TSOH as your acid to deprotect it.
Because like the steps are just the same. Like
Yeah.
water back
Yeah, they're literally the exact same. So it doesn't really matter what acid you have. H3O plus was just to signal to you that you have cationic acid already in solution. You're just going to go backwards, adding water. Yeah.
What's the same class that he won't ask you if you just say HA for acid?
Well, at the same time, it's a multiple choice test, you know? So it's not like you could just write HA on there. He'll give you acids, and you'll have to know that they're acids. That's why I am signaling like TSOH is an acid and H2SO4 is an acid. Because you'll just see them as a list. He won't write HA. That would be really nice if he wrote HA, but he does not. Yes.
Alright, so the example that you used in class where you had 2 ketones kind of in a row,
Yeah.
and then if you weren't to use this, it would attack on both. Would it attack to the point where both ketones would have 2 substituents, like 2 added carbon groups, 2 added carbon groups?
It depends on your reagent. If you
If you use organometallic,
you only have 1 hydrogen left at that point. You only have 1 bond you can make. So each of them would only have 1 additional. The reason why you can put 2 substituents on those groups when you make acetals is because you're taking the entire carbonyl carbon basically and kicking it off and making 2 new carbon-oxygen bonds in the place of 1 carbon-oxygen bond. That was double bond.
you're getting rid of the CO bond.
Yeah. Yeah.
What if it was 2 ketones then?
I don't think he'd give you that because you'd protect them both in that case. And then there would be no point.
You just use one of them, right?
Yeah, what he did was he had a ketone and an ester.
Yeah.
And it doesn't protect the ester, but it protects the ketone. Because the ester has another O bond that can kick off as a leaving group instead of the water. So it's not actually a reactive acetal protecting group. But the ketone or the aldehyde are because they don't have good leaving groups. So you can just kick the carbonyl oxygen off as water. Does that make sense?
Yeah.
So if he asks you to protect an aldehyde or a ketone, it's going to be 1. And then you're going to have a different reactive portion that's unique. It's not going to be, yeah. Because if you had 2 ketones or an aldehyde and a ketone, they'd both be protected and then that was pointless. Yeah.
Would the alcohol you use to make your acetal, can you technically react with like
that that's actually a good question.
Every example he gave us, we had an ester with a ketone, and so.
Yeah.
like-
Yeah, I don't think he'd give you a question where it's an acid chloride, because it would make, unless he wanted you to make that. Because he could ask you to make an ester from an acid chloride. That's actually a really good question he could ask. But like, he could ask you to make an ester from an acid chloride, and then have a ketone on the other side that didn't react. So then you'd need to do the protecting, and in the act of protecting, you'd be making the ester as well. It's a cool thought, yeah.
So, I'm sorry, I'm just confused. So the deprotecting, I know you use an acid, but where in the protecting process would you use the
TSOH. So it is the thing that protonates the carbonyl oxygen enough to leave as water. Because the carbonyl oxygen doesn't have any hydrogen bonds at first. So it becomes an alcohol, and then it becomes protonated enough to leave as water. And then the acids are really versatile. They're super helpful for deprotonating and protonating when you need them. H2SO4 is a great example of that, where you can use it to deprotonate and then protonate and really basically just do what you want. Yeah.
What other acids does he like to use? Just to know.
The only ones I can really think of are TSOH, H2SO4, and H3O+, which is just HA. Basically, H3O+ is his version of HA. So it's just acid. So there's really no like specifics about what type of acid that is. Okay. Any other questions on this? Feeling good? Okay. Sugars. First of all, please don't freak out. You guys are not going to have to name a sugar. You're not going to have to know pyranose, furanose. That stuff's all for biochem. I would be very surprised and a little bit irritated if you put sugars on your exam, because I have never been tested by Dr. Price on sugars. I think the reason why he did this is this, because I think he wanted to clue you guys into the fact that acetals are the reason that sugars cyclize. Hemiacetals and acetals are the reason why sugars cyclize and why they connect. So sugars are never found just like in their linear form, hardly ever, like especially in your body. 99.9% of the sugars in your body are cyclized. Those cyclized sugars are always found in chains. Like you have to use very strong enzymes to break them apart from the chains that they make. And the reason why they make chains is because the chains are made with acetals. And the reason why they cyclize is because the cyclized form of a sugar is a hemiacetal. So cyclized hemiacetals are more stable than uncyclized hemiacetals. And then acetals are more stable than hemiacetals, which is why they cyclize, or why they connect in chains. Yeah? You have a question? Yeah.
It's probably a really dumb question. I know you talked about it.
Hemiacetal is where it's an alcohol group. It gets like a O bonded to an R group. And then the next carbon is bonded to an OH. Yeah. So it's not two alcohol bonds. It's still an acetal because it's an oxygen and an oxygen. Like there's two oxygen carbon bonds. One of them is an OH, and one of them is a alcohol. Which you end up making a hemiacetal in the acetal formation, because water is still bonded when you attack your first alcohol. Once you protonate it and kick it off, then it's no longer a hemiacetal. Other questions? So this is the application. I really don't see him going any further with sugars in this. I think it's just why, I think that is why he talked. I would review them though, just so that you understand that concept and how they apply. Okay, hydration. He talked about hydrating, which it's like almost exactly like acetal formation, except it's OH groups bonded instead of alcohol groups bonded. So it's literally just like, sorry this is so unorganized, but it's really just this with 2 OH groups coming out. That's a hydrate, or a gem diol, is how the fancy chemists say it. Yeah?
And you would make that with just acid and water
Mm-hmm.
with like an ester?
Usually aldehydes. Aldehydes and ketones are the reason why he used this. He also referenced taking an enol and tautomerizing it to this and then hydrating. That's how he talked about this. So I would just be aware that this is a way in which it applies. Like you take an enol, you tautomerize it into an aldehyde or a ketone, and then you can hydrate it if you still have.
Can you show that?
Yeah. So if you have this, you can tautomerize it into this. And then you can react that with, in fact, I'm pretty sure he only used water. Yeah, I was gonna say, he only uses water to do hydrates. Because you don't really need catalytic acid, because this comes in attacks, this comes up, and then you just have water in solution to protonate this one, and then you have a deprotonated water to deprotonate
Wait,
this
but
one.
water, can water attack if it's not frozen?
That was what you were talking about, like,
I feel like it has to
tiny
be
bit of
frozen.
H2O plus sodium solution. Like,
Oh
10
yes,
to
like the
negative
10 to the negative
and
7.
that's what protonates it, and then the rest is water.
Hate that. So hard to explain that. It's really just because there's some acid that's left on your container from the reaction that just happened. It's so hard because how do you assume that? Anyway, just assume that, I guess, that you have, whenever you need to protonate an oxygen, assume that you're going to have the needs to do that. Does that make sense? But, it does have to be protonated. You're right. Yeah. So it does have to be protonated. This can come in an attack, and then you have the water in solution to protonate it, and then the deprotonated water in solution to deprotonate that. Yeah, to make this. Yeah.
So he would show the coordination step like that?
Yeah. He would have he would probably indicate it as 10 to the negative 7 acid. H3O groups. Yeah. Okay, and I just took this quote literally from the study guide with regards to hydrates. It's literally one little section, so I would be very surprised if if this was a substantial part of the test, but it could be at least a question. In the study guide, he said it can proceed in either acid or base catalyzed conditions. So technically, if you have OH minus in solution, which that confuses me, because you do still have to protonate that. But, yeah, you guys are so good. I'm so tired. You guys, I know this stuff, but I don't have to, anyway. You guys are really smart. Okay, so yeah, if it's OH minus, then it can just attack. It doesn't need a protonation step. And then the electrophilicity of the aldehyde determines the equilibrium, so how much you end up getting. So if you have a more electrophilic aldehyde or ketone, then you form a large percentage of hydrate at equilibrium. So that's usually if you have an electron withdrawing group attached.
You have chlorine on there, you have more.
Yeah. So you could have a few different types of molecules with different things that change their electrophilicity, and you could have to determine which one would make more hydrate. This type of question you could be asked. And again, the reason why he talked about this was he talked about enol tautomerizing and then this happening with water and acid in solution. So, questions on this? Again, it wasn't a super huge part of the study guide, and he spent 5 minutes in class on it, so I don't think it would be a huge portion of the exam. But this, however, please remember this. If nothing else, remember this. This is Dr. Price's favorite thing. He I'm actually really disappointed that he did not make this more apparent when he taught this, but maybe he did. I don't actually think I was here when he taught this part, but he loves imine formation. He went into like great detail about it in the major section. So he really likes these. So please remember this. You only make an imine with primary amines. Why is that? 2 H's. And why do you need 2 H's? Yes.